So we are wrapping up Chapter 6. Next class period will be review, and then we'll have an exam. And we are talking about the Ehrenfest classification of phase transitions. First order phase transitions. If you have a first order phase transition, ice is melting. Is that a first order phase transition or a second order phase transition? Did you grasp that from the reading?
Where the first derivative is discontinuous is first order. So it would be first order?
Yeah, melting. The phase transitions we're used to is that we kind of experience in life here are first order. And it's kind of interesting. I mean, if you have a pot of boiling water, right? So the water is going from liquid to vapor. What's the heat capacity?
4.1.
Now there's this number 4.184 joules per Kelvin per mole. That's the specific heat for water. And that's if you want to raise it a degree. And that's assuming that it doesn't change over a temperature range, but that's what that number was for. But if you're boiling, what's the heat capacity? Because if you apply more heat, does the temperature go up?
No.
No,
Boils.
but you get more what?
Gas.
More gas, right? So give it even more heat. You get more
So the heat capacity
vapor.
is more than point.
So what is the heat capacity? That's the question. You just applied more heat. Temperature didn't change.
So the critical temperature?
If you apply more heat, temperature's supposed to go up. That's what heat capacity is all about, right? But if you apply more heat, temperature doesn't even budge. What would be the heat capacity?
Of water at 100 degrees Celsius?
Well, that's the boiling point at 1 atmosphere, if the water's pure.
That's not the same as the
But
heat
what's...
capacity?
No, heat capacity is kind of what Kevin was talking about. It's that, you remember, like, specific heat or heat capacity. If you remember doing problems, it was like 4.184 joules per Kelvin per mole, and that's the number that you use to raise the temperature of water so many degrees, and then you can figure out the mass. But that's liquid water. And you apply that heat, and that amount of water will go up that temperature using that number.
Oh, so it's 0.
So if it's zero, so go back to boiling. If it's boiling, if the heat capacity is 0, well, it's just the other direction. Heat capacity needs to be really, 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 really what? High. Because you're putting in all of this heat, and the temperature's not even budging, right? So but does it ever go up? Is it a million? Is it a gazillion? The temperature never goes up. All that energy goes into what? When you're boiling?
Converting the liquid to vapor.
Converting liquid to vapor and giving it its kinetic energy or whatever, right? Pushing the atmosphere out of the way. So again, what's the heat capacity? It's infinity. It's infinity. So first order phase transitions, it's infinity. If it goes back to making, let's say we have a compound, and let's say let's make up some stuff here. Let's say the freezing point is 3 degrees Celsius. Let's say the boiling point is 80 degrees Celsius. I'm just making stuff up. And you can always complicate life. You can say, oh, you have 250 milliliters, and this is the density, and these are, but all I'm really talking about is a homework question that wants you to write as time progresses, what would the temperature plot look like? Right? And they're going to give you a start. Let's say you're going to start at like -10 degrees Celsius. and then you're going to stop at like, I don't know, 100 degrees Celsius or something. Okay? So you put your -10 on here, put your 100 on here, and then you're supposed to just sketch it and what it would look like. So you start at the -10, of course, but how do you draw the line? Then you draw the line to what and do what? Now this compound is obeying first order phase transitions. It could be water. It could be whatever compound. Well, it's not water because it doesn't freeze at 3 and boil at 8. But
It would go from the -10 up to 80 and then make it discontinuous.
okay, we're getting there. So you're gonna heat. So let's start at the very beginning. Though. If you're at -10, it's a solid, and you're heating it up. So the temperature is going to go up. Is it going to go linear or is it going to go kind of curvy?
Curve.
Technically, it goes kind of curvy, but I don't know if you can even tell if you plot it out, right? You might if you really zoom it up, but okay, so fine. Let's say it goes a little curvy, and it keeps heating up until you hit what temperature?
80.
But you're below the freezing point.
Oh, freezing point. Yeah.
So it's going to go to TF first. And then once you hit the melting point, remember heat capacity is infinite, so all the heat goes into converting it from phase to phase, in this case solid to liquid. So the line is going to be flat as a rock, until all of that solid is liquid, every single little cubic bit of it. So this has to be what temperature? 3. Okay. There you go. It's going to go up again, kind of curvy-like, until it reaches 80. Okay. And then it's a flat line until all the compound turns into a vapor. Okay, now this is where I don't know, I think we probably should have been a little more careful, but that's okay. We can kind of still express it. Now, have you ever been cooking and you get your hand where the steam is? It's as hot as an H, yes. So steam can get hot really, really fast. In other words, it would have a heat capacity that is very high or very low.
Very low.
Very low. So when you sketch this out, that should be a pretty steep line, because that steam heats up real fast. So it's a really steep line, right? I mean, that steam gets hot fast. So when my wife is sitting there cooking macaroni with the stove cranked way up to super high and the burner's all hot, just red as glowing, does it help anything other than make it a dangerous situation, because the steam's going to burn the hell out of her if she gets her hands over it, right? It can't increase the temperature any, because the temperature is the boiling point. All it's going to do is make that vapor extremely hot. And I guess maybe the vapor kind of gets in the way of the macaroni. I don't think so, though, but maybe a little bit. But you're not really helping anything. So once you get something boiling, that's all the temperature you need. This is the point, though. That's the homework. And discontinuous. So this is one example of discontinuous, right? Slope changes pretty quick. What's another way a plot could look and be discontinuous instead of this? So this would be, I guess we should put in our axes here. Right? Would be another way it could be discontinuous, a discontinuous plot. It jumps, exactly, it jumps. So draw a plot where it jumps. So it's coming up, right? Something like this, I don't know, it jumps. Second order phase transitions. Pretty odd. I think I read that superconductivity as a second order phase transition. So there's no energy in going into rearrangement of atoms. It's more like a property. Some property, all of a sudden, boom, there's this property. And so it's not a very, something that we can really imagine. But superconductivity is one of them. And why is this a holy grail of these ceramic chemists, especially nowadays? What are they trying to do? Right? What is superconductivity? The reason why I mentioned ceramics is because the goal is to find a compound that exhibits superconductivity at room temp. If we have these power plants out at Calaveras and Browning, they got all these power lines all over the place, right? Well, they're generating the power, burning a lot of coal, right? Generating a lot of electricity. And remember how? Get something boiling, get a turbine spinning. You have a turbine spinning. Inside you have some magnets with coils. Moving magnet inside a magnetic field generates electricity. Okay, we'll go over that one more time. It's better to go with pictures, so we'll go over that one more time. But the point is that it's going to generate some electricity. Well, he has to get to your house. It has to go through the power lines. Well, there's the R word, resistance, right? So what if there was no resistance? So it'd be interesting to look up the energy that they lose through resistance, but it's a good chunk. It's a good percent. So make all these lines out of this material that's superconductive.
It's like the commercial where they talk about the grid and how like a lot of energy is lost as power is sent out and stuff.
It could be that it could be that there's probably more things than just resistance. There might be just losing it
for a number of reasons.
Poor connections or static, whatever. So there might be more than one reason. But superconductivity, no resistance. And what they think happens there is that in the material that the electrons pair up so that they're almost an imaginary line between them. So as they collide, instead of reaching resistance, they get elastic collisions. The angular momentum's conserved somehow. And that's kind of the picture that goes through my head for superconductivity. And I don't know if that's right or not, but that's what they think. And they've reached liquid nitrogen, which is a huge deal, but they're not near room temp yet. So that's kind of where they're at. So you've probably heard of these huge NMRs, which we don't have. They're several, like $100,000 plus. And their resolution is so much better than what we have, and you take instrumental and you find out more about that kind of thing. But yeah, you need to have liquid nitrogen the whole time, though. Otherwise, it's...
Why does that make it easier?
Because they use superconducting magnets. Mm-hmm. And it's not going to be superconducting. It's not going to work if you don't cool it below liquid, if you don't get it to liquid nitrogen temperatures. It'll be just like ours upstairs. Just a big hunk of, just a big magnet. I don't even know if it would work. Well, that's a good question. I don't know if it even would work if it's not cold. But that kind of increases the cost of that stuff. And it's super expensive in the first place. And all we have worked, so why mess with it? Okay, what else have we talked about here? We talked, well, there's these lambda transitions. So we kind of saw one. I mean, where did that go? For helium or something? Yeah, our lambda line for helium. So there's a lambda transition. So I don't know. What can you say about it? I think the heat capacity changes. There's a change of state, but it's
like instant kind of.
Yeah, there's. It's hard to relate to it because how do you relate to something going from a solid to a gas, but it can't be a liquid? It can never ever be a liquid.
It's almost just like the temperature range over which it changes. See how it's like there's a little bit of space between these two lines, so it's like
somehow
half a Kelvin.
You try to melt liquid helium. You try to melt helium.
Solid helium.
It goes right to a gas. You can never see the liquid phase. So
it has to go over that little range in Kelvin, right?
yeah, it looks like there is a small
Yeah,
change.
so it's almost like it has to like have that heating up.
Yeah.
To make it happen.
Yeah, I really don't know much about lambda transitions. I remember I had to play with liquid helium once. I got in trouble. But
You were breathing it in or what?
no, it's called a whole burning spectroscopy, and it's pretty expensive. So, because you have to have liquid helium and then get things, it's almost like it's not that complicated. Here's an absorbance spectrum. Okay, you get this substance at liquid helium temperatures, and then you pull a vacuum on it. So now it boils at an even lower temperature. You're like less than a degree above absolute zero, and that's where you immerse this material in that substance. And then you shine a laser on it. So then what happens is maybe the wavelength is right here, and you saturate it, so then it absorbs, but then it won't go back down to the ground state. It'll stay excited. So then the absorbance spectrum, you can get a lot more information and fine detailed information from doing whole burning spectroscopy. And what they were really messing with is trying to figure out photosynthesis. That's what the real goal was. And because you can figure out photosynthesis, my gosh, there goes all of our energy problems.
Right.
So that's what we were working on, trying to build a man-made photosynthesis machine, but to figure out how photosynthesis works in the first place, and how one state goes to another state, and the interactions undergoing, the underpinnings. Okay, where are we? Surface tension. So if we have time, we'll do Mungia's surface tension lab. And at least you get to play with lasers in there. It's kind of fun. We'll probably do it as a group if we have time. But what's W? W's work. What's sigma? Now, area. Because surface tension, right? Right? It takes work to stretch a liquid. And it's going to take more work to stretch different liquids, right? So surface tension is our gamma, and it's just so many joules per square meter. And the little expression here, the little d means differential, right? So if you stretch the surface of a liquid a little bit, take some work, but stretch the surface a little bit, right? Take that area, whatever you increase it by, times this constant gamma, the surface tension, and then you get the infinitesimal amount of work. So W is gamma sigma in macroscopic. So all these surface tensions, right, they're just tabulated. It's a intensive property of a substance. Okay. Okay, let's not do that first. Let's jump down to this Laplace pressure thing. See if this works. I was working. This is why I kicked you out, Kevin, because I was messing with this, trying to get this to work. So both syringes are filled with air. And they're putting soap on one of the syringes, right? The little soap down there. Make a little bubble, right? They pushed in the syringe. Okay. Right, you make a little bubble on the other side. Okay, so, but this tube is sealed. These little valves are sealed. So he made a little bubble on this side. So he's got a little bubble over here and a big bubble over here. And then he's going to open this little valve so that the air here is open to the air here. What's going to happen? Anything? The answer is in our equation. The answer's in our equation. Let's see if you can figure it out before we show you the answer here. Is the pressure inside a bubble the same as the pressure outside a bubble?
No.
No. Which one's greater? inside. Why? Because inside is the outside plus some number, right? So the inside's definitely bigger. And what do you think little r is? Radius of the bubble. So you can get some pretty big differences here between the inside pressure and the outside pressure of a bubble. Because dang, look at that. I mean, you get a small bubble. Okay, so back to this picture. They're going to open this valve. So what should happen?
Pressure should go from high to low, so it should even out the two bubbles.
So which one's going to go? The pressure here is
lower than the pressure over there. Because diamond's on top.
inside is, but the bubble's a lot smaller.
Radius, yeah.
So which one has a, that's the real question. Which one of these has a higher pressure inside? The little one. The little one has a higher pressure inside. So what should happen?
So it should make the other bubble even bigger, right?
It should make this one even bigger. It's the opposite of what you'd think. You'd think, you know, we're so used to things leveling out,
Yeah.
right? You can picture this guy getting bigger and this one getting smaller because then it just should level out. But no, the smaller the bubble, the higher the pressure. Now he's opening this little valve there, and there it goes. All right. Whoop.
So it's easier to make a bigger bubble than a smaller bubble?
I don't know what's easier. It's just that's nature. The smaller the bubble, the higher the pressure inside. They call it the Laplace pressure. That was right down here. Okay. And I think I should write some of my own homework questions because sometimes the book doesn't go far enough. But if you have if the radius or the diameter, let's stick to diameter. I think the diameter is around 1 millimeter. You don't see much difference. But if you get it down to the width of a hair, about a couple microns, now the difference is going to be over an atmosphere. So that's like 1,000 times, right? 1,000 times smaller, millimeter to a micron. Okay, so what does, these pressures can really get much, much higher. And in fact, I think some folks are doing research on this, and especially I think they should go back to this kind of stuff. This physical way of killing bad stuff makes more sense than the chemical way, because it's better for the environment. It's going to work all the time, no matter how bad the bug is. So the idea is you have all this bacteria, and instead of having medicine destroy it, we're going to have these extremely small bubbles. So these extremely small bubbles, the bacteria gets inside the small bubble. The bubble's such a high pressure, it just crushes everything. Can't exist. So it's kind of interesting, I think. But it must be more difficult to do because I don't hear about it at all. Okay, so let's move on from bubbles to droplets. So this is vapor pressure. Okay, so P star, let's just focus on something, water. P star would be the vapor pressure of, well, P would be the vapor pressure of the droplet, because that's what the equation says. But P star would be
Pressure of the water.
vapor pressure of water, the typical vapor pressure of just liquid water. You get it from a table, right? At that temperature, whatever the temperature is you're interested in. Okay, but they're saying that, you know, and look how these droplets, look at R's in the denominator. So this is really exacerbating itself, this vapor pressure increase. Because if you make, not only is it exponential, but it's exponential with the radius of that droplet in the denominator, so that exponential gets even higher and enhances itself. So this vapor pressure can just skyrocket really, really fast. So if this vapor pressure gets really, really high, that means that
The radius is really, really small.
yeah, the radius is really, really small, but it's the only way that I can really figure out how this actually works, this whole idea of clouds. Because what they believe is that there's several theories. And the theory I'm talking about is this Bergeron theory. And it's I've always been fascinated by this. If, according to the Bergeron theory, we're talking about rain, snow, hail, whatever, precipitation, how does a cloud bloody well work? Well, they believe that, okay, here's your typical cloud. But the point is you need this super saturated air in this cloud. You need super saturated air. And I've never really understood, how the heck did he get super saturated? Because what does super saturated mean?
Oversaturated, like above its capacity to hold water?
Above its capacity to hold water. It's a very unstable situation. How do you get it? You get it by having extremely small droplets, because then their vapor pressure is extremely high. So you can generate a supersaturated region, okay? And, okay, that sounds great. Well, then how do you get the rain? How do you get the little particles, the snow or whatever, right? That's where this kind of demonstration comes in. So if you, the Bergeron process, we need some air, so we got some air, right? And then I need some water, vapor, technically. So let's put some water in there. Let it evaporate. Well, you can't stop it. It's already evaporated, right? So I've got a container with water vapor in there. I probably didn't even have to put the water in there, but it really helps if you do. Now I need some wind, pressure differential. So if you can't see, you might want to move. So what's a cloud look like? Should look kind of what if I make this, Kevin?
Cloudy.
Should look cloudy. Jeez, Padawan. Well, kind of, maybe, right?
Mm-hmm.
What's missing are spontaneous nucleation centers, right? Or nucleates. Or I forget, there's another word for it. But what I'm going to use is smoke. So I get this going pretty good. All right, and when I drop it in there, you see a little puff of smoke. See a little puff of smoke? So let's try the same thing again. So in my okay, so now you got your cloud. So the point of all of this is that inside every single raindrop, every single snowflake, every single little thing that's precipitation, is a nucleate, right? A little tiny particle of something. Now, you take a whiff of this. Is this what our atmosphere smells like? So definitely inside little raindrops is not smoke. It's what?
Nitrogen, carbon.
It has to be a particulate matter. It has to be nitrogen, carbon. That's what air is in the first place, though. Carbon dioxide. No. Dirt. Well, then it would work. It would work. I'll give you a hint. Our world is covered by 3/4 of this.
Water.
More specifically,
Ice, is that the particular
more. It's not cold enough for. Because I couldn't have made ice. What's in this 3/4? Salt water, okay. What happens with the oceans? When you have 3/4 of the planet's covered with this, sun's beating down on it, water evaporates, where's all the salt go?
It stays in the water, it stays down.
Well, it kind of gets picked up in the air too. But it kind of gets in the air too. That's what they say. That's the particulate matter. So whenever you're getting raindrops on your tongue, it's really salt water. Why doesn't it taste salty? It's extremely small, right? It's a nucleate center. It's an extremely small crystalline hunk of salt. So you can't taste it. It's like pure water, right? So that's what's going on there. You guys weren't with me for this, were you? I haven't played with this in a long time, so I was hoping someone was. They remember what to do with this. So this is some sand. So we're talking about surface tension now. Here's some water. All right. This stuff is just, right? Look at that. Isn't that weird? Let's get it out of there. Oh, it fell through. Shoot, it's not supposed to do that. But the point is it's what? It's dry. Right. That stuff is dry. It wasn't supposed to fall through there. Right? So it's just coated, it's sand coated with this organic material.
This is so non-polar, the water falls right off.
Yeah. For example, what I want to show you is, so here, this is, whoa, what happened there? This has a lot to do with the project that I mentioned that Mungia got. And the idea is you can figure out surface tensions by measuring the capillary rise height in the capillary tube. And you just have to know you have to know the density, you have to know gravity, you have to know the radius of the capillary tube. The capillary tube can be really expensive if you really want to know the radius of it down to it. So why not just go get any darn little glass tube, shine a laser through it, get a circular diffraction pattern. From that, you calculate the radius. And that's what the experiment's all about. But so the point here is we're still talking about surface tension. The whole reason for all of this Laplace pressure we talked about, the difference between the inside and outside of a pressure of a bubble, or if you're talking about water droplets, or if you're talking about capillary rise, it all has to do with surface tension. So if you take this is kind of old research, but it's still fun to play around with. What happened to the other one? Oh, I had 2 glass slides. Oh, here it is. Thank you. Yeah. Okay. So the idea here is, I don't know. I still don't know why they don't do it. If your windshield, your bathroom mirror, whatever, you don't want to fog up ever. You coat it with an organic compound, but the point is the organic compound is this big, long organic chain. But on the end is silicon and oxygen. So it actually will become part of the glass. 'Cause that's what glass is, right? Silicon and oxygen bonds. So at the end of this big, long chain is silicon and oxygen. So under the right conditions, this big, long chain will react with glass. It's a boiling process. At least that's how we made these, is a boiling process. And we put the compound in, and there's several steps to get the reaction to progress. But it's the same steps that in instrumental analysis we talked about how, I think that's why we use this. because we talked about how in the capillary tube there's the mobile phase for gas chromatography. And they have to somehow physically attach that material to the capillary tube. Or in liquid chromatography, they have these little tiny glass beads, and they put the stationary phase around it. How do they attach that stationary phase to those glass beads? It's a silicon-oxygen chemistry that we're talking about here. So what I wanted to do is just show you this idea of contact angle. Some of you have seen this, some of you haven't. If you take some water, put it on a typical glass plate, right? That's what it looks like, right? But if you take the same material, same glass slide, but you coat it with this organic material, right? That, why don't they put on all these, especially windshields? No, easy. I mean, this is part of the glass. You can't scrape it off. You can't, it won't come off. You have to actually etch the glass to get it off.
You think that is like an upgrade?
I just think how much easy bugs would come off, all that stuff. You wouldn't need windshield wipers. That would.
You're right.
See the difference between the two, right? It's really beat up. So you get your little microscope from biology or whatever, and you measure the angle from the contact angle. It's a much higher angle, right? But it's gone. Just have a little gravity. I guess maybe it does kind of stick if it would get dirty. So you might still need windshield wipers. But that's very different than this. And they're both pretty dirty. I mean, I haven't cleaned these things for... Okay. I think that's about it. So 6.8. Refer to figure 6.5 and describe the changes that would be observed when water vapor, 1 atmosphere and 400 Kelvin, is cooled at constant pressure, 260 Kelvin. See, so this is that problem that we talked about at the very beginning of the hour. Draw a cooling curve, temperature versus time plot. So the information you need is pretty much where's the boiling point, where's the freezing point.
Mm-hmm. It's just
and then you just sketch
0
it.
and 100 degrees Celsius plus whatever it is in Kelvin.
I think you're right, because it's that 1 atmosphere.
Mm-hmm.
So it should be typical. It should be typical boiling and freezing points.
Okay.
And they just have that weird Kelvin instead. So you're okay with 6.8? So we don't need to sketch it, do we? Let's take a look at 6.9. Naphthalene melts at 80.2 degrees Celsius. If the vapor pressure of the liquid's 10 torr at 85.8 and 40 torr at 119.3, it already sounds like they're setting you up for what?
Clauses.
Yeah. Oh, there it says Clausius Clapper. Because they're giving you temperature and pressure conditions, right? Calculate the enthalpy of vaporization. Normal boiling point. This sounds like last homework, right? How would you do C, though? What is the entropy of vaporization at the normal boiling point?
You use that delta S transition with delta H transition with delta T.
Yeah. Well, it's really not a delta T. Do you see what he already said?
Delta transition T.
It's just T, because the temperature doesn't change. So it'd be delta S is really Q over T, but your Q is your delta H, so delta S is delta H over T. That's how you do C. Okay.
How do you get B then?
B, the norm. I would use that Clausius-Clapeyron equation, right? And use one of these points. Right? Normal boiling point is what pressure?
1 atmosphere.
1 atmosphere. So then you just find T2. But yeah, it can't be 1 ATM though. It has to be in what units? Pascals. And then you'll be okay. So are we okay with 8 and 9 then so far? What fraction of the enthalpy of vaporization, now I think we're getting into something that's a little more interesting here we haven't seen. What fraction of the enthalpy of vaporization of water is spent on expanding water vapor? So the fraction would be, what would be on the bottom?
Whole.
what would be in the denominator of this fraction?
Entropy of the vaporization.
The enthalpy of vaporization of water. So you got to just look that up and put that number in here, right? What are the units for that? Something like that, right? Isn't that always in typically like kilojoules per mole? Okay. So our problem is to figure out the top part, right? What fraction of the enthalpy of vaporization is spent on expanding the water vapor? So you're expanding the water vapor. The water vapor is pushing against what? You have this liquid, turns into a gas. Well, it has to go somewhere. The external pressure, the surroundings, right? It's pushing the surroundings out of the way. So if you want to vaporize something, yeah, you have to, the actual intermolecular interactions is changing. You're turning a liquid into a vapor, so you have energy going into there. But there's a fraction of this that's also just, you have to push the external pressure out of the way. So what equation was that?
It's not Px delta V, right?
Yeah, it is.
Yeah. How do I know the delta V?
Good question. Px is going to be what, though?
Yeah.
1 atmosphere, but in pascals, so that we know that. What is delta V? So it'll be P external, V what minus V what?
Vi minus Vi.
Yeah, oh yeah, you can say Vf minus Vi. But that's equal to Px more,
Vf.
what is Vf? We're going from a what to a what?
We're going from a liquid to a gas.
Liquid to a gas. So it would be V,
Vg.
Vg, or V gas, minus V,
Vl.
Vl. Okay. Are we supposed to have a minus sign here? Okay, now the next step, the work that we're going to put up here
Negative Px Vg.
is approximately negative Px Vg. Why can you say that?
It's gas, the volume's going to be small.
Yeah, the gas volume is so much larger in comparison to a liquid. Okay, you told me that you know how to get Px. How do you get Vg?
Ideal gas law.
Ideal gas law, man.
You're killing it today.
I know it. Okay. So, Shelby, we're going to get V using the ideal gas law. I like Eric's idea. Do we know everything else in there? In that equation, in the ideal gas law equation, do we know something to plug in for P, N, R, and T? T would be in Kelvin, good.
And then the P is 1 atmosphere.
Yep.
And then N would be 1 kilos per mole.
Good. She found, I think that's the trick. N has to be 1 because look at the enthalpy of vaporization is per mole. So you have to somewhere, right, assume N is 1 mole. So then you're going to have just kilojoules in the denominator and get get the work up in the numerator. So you have to assume N is just going to be 1 mole. Right. So then this denominator will just be kilojoules then, because you're just using 1 mole.
Do I use 8.314?
If you use 8.314, that's when I would definitely use, because then work is in joules. But then volume has to be in cubic meters, right? And just watch them all. Okay, we're good? 12. Calculate the vapor pressure of a spherical drop of water. Okay, where the heck is that equation? Okay. Can I just click on that? This might save some time. Ooh, nice. Okay, there it is. Calculate the vapor pressure. That's what we want to do, right?
Mhm.
There has to be something in here. Because is it just a straight, let's pick on Mel. Mel, is this a straight plug and chug where all we do is find P and it gave us everything and we don't need to worry about anything? Is there some trick to this? Ah.
You have to convert the density to thermal. So you're speaking.
Okay. Exactly. Very, very good. Now, did you see everything up to that point, though? Let's make sure. We got to convert, well, not really centimeters cubed per mole, meters cubed per mole. So how do you do that?
Molar mass of water.
Yeah, pretty much that density, we have to first what? Flip it, and then just play with your units. Convert cubic centimeters, cubic meters, and grams to moles, and you got it. Okay, how about this P star?
Isn't that 2.3 kilopascals?
Except, what do you do with the kilo?
Okay, just pascals.
Oh, you could leave it there, couldn't you? And then P would end up in
Kilopascals.
kilopascals. That would work. Jeffrey, let's pick on you here. How about, what are you going to plug in for the surface tension? Well, that is a good one.
Joules per meter squared.
I guess they expect you to what?
Calculate.
Not calculate it. I think,
This equals joules per meter squared. Can we get that? Radius 10.
well, but remember, surface tension,
Oh, we looked it up in
look it up in a table. Surface tension, enthalpy of vaporization, they're all properties of substances. So I think they're expecting you, since they told you what the compound is, they're expecting you that you can look up anything and everything about water. Since they told you the compound, they're assuming you're going to just do that. Shelby, what are you going to plug in for? So we got that done. We got V. What are you going to plug in for R?
Oh, little r.
That little r. Yeah, but exactly what you're going to plug in. You're not going to plug in 10 nanometers. You got to plug in 10 times 10 to the negative 9, because nano is negative 9. And that's about it, right? R and T, good deal. T in Kelvin. Okay, we're about out of time. So these aren't so bad.
What was? Okay.
All right, we're going to fly in this. So have a good weekend.